So in our recent class last Tuesday, we talked about some of our first radical rules. We talked about the radical of a product as a product of radicals, and same thing with the radical rule number 2. We said just split up the fraction, take square root of the top, square root of the bottom, for example, or cube root of the top, cube root of the bottom. Today I'm going to introduce the third rule as I'm slowly, hopefully not lagging out too much here. The third rule I refer to is this is the phrase that pays. I've got it in quotes up here on my screen, power over root. Okay, so if you can remember this phrase right here, power over root tells us how to convert something from what's called radical form into exponent form. Okay, so what I mean by radical form is like if you've got something where it's a square root or it's a cube root or it's a fourth root or whatever, yada, 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 and you convert that over. Ooh, I'm lagging pretty bad. Okay, you convert that over into exponential form. Can you guys hear me all right?
Yes.
Can you see me okay? As far as like what I'm putting on my screen?
Yes.
Okay. So I know the video's kind of out of sync and lagging. I apologize for that, but I think maybe since I'm running a recorder outside of the Microsoft Teams program, maybe that's what's doing it. Anyway, the idea, the notion here, fellas, is to be able to take something like the square root of x and to write that as x to a power. Okay, so like look what I've got down here. I've got the square root of x. Remember the phrase that pays is power over root? That's the same thing as x to the 1/2. Okay, again, where the power was 1 and the root was 2. So something like the cubed root, in this case I've got down here the cubed root of x squared. That's the same thing as x to the 2/3. Okay, now this is where our normal notion of exponents sort of breaks down, doesn't it? Because like if I asked one of you guys, hey, what is what does an exponent of 3 mean? You say, well, okay, well x to the 3 just means that I multiply x times x times x. Okay, well if I say what does x to the 1/3 mean, that doesn't all of a sudden mean that you you erase 2/3 of your letter. That's not what that means at all. Instead, what that means is that you are raising something to a fraction, and therefore you are dealing with a radical. Okay? So our normal sort of counting way of thinking about exponents breaks down here, but what's nice about this approach is that all of our exponent rules, the rules that we learned back in chapter 4, all of those rules can now apply with radicals. Okay? So, that being said, I've got a slew of examples, and here's where I'm going to cold call on some folks. Like even just right here, looks like I've got 15 examples that we can go through. So I'm just going to kind of cold call on some folks and see if you guys can help me out with some of these simplifying ones. All right, so we'll start with Grady. Square root of 144, Grady.
12, so 12.
Yeah, just 12. So in other words, what we're asking is we're saying, hey, what non-negative number, when squared, equals 144? Okay. How about, oh, Grady, that was good. Thank you very much. Cullen, what about you on the opposite of, or negative, and then square root of 289? What about that one? What do you think negative, bless you, square root of 289 would be? Cullen, your mic is muted, by the way.
The negative square root of 289.
Mm-hmm. So I know my answer is going to be negative. What's the square root of 289? Is that one you've got memorized?
No, sir.
Okay. John, how about you? You got square root of 289 memorized?
Is it 17? Negative 17?
Yeah, it's just going to be 17. So square root of 289 is 17. If there's a negative coefficient, then we just say, okay, well, that's a negative. And again, fellas, this will go back to, and I'm not busting anybody's chops, obviously, because we're first working with this. But this goes back to memorizing our perfect squares and our perfect cubes, and trying to have those down just to where you can at least recognize and say, oh yeah, 144, that's a perfect square. Or, oh yeah, 289, that's a perfect square, right? If you kick over with me to the right side of your screen, you see example 8.3. If you look at those, let's see here. How about, Jack, did you ever pick up with us? Are you on here?
Yes, I'm here.
All right, Jack, what's the cube root of 64?
4.
All right, good. 4 times 4 times 4 winds up giving us 64. And so that winds up being the cube root of 64. Very nice. How about, Nick, you got the 4th root of 81? What non-negative number, when multiplied by itself 4 times over, equals 81?
3.
3, yeah, very good. And then lastly, how about the 5th root of 32?
My mind went blank over Wednesday, so I forgot all of this.
That's all good. Think about it. Can you think of a number that when you multiply it by itself 5 times equals 32?
Is it 2?
Mm-hmm. It absolutely is. Very good. And so when you guys see examples like these two that we've done, example 8.1 and 8.3, what those are examples of is where the numbers work out nice and neat. And so you very well likely won't see a lot of those in an algebra lesson like 11.3 or 11.4. They're most likely going to give you ones where they don't simplify out very well. So you guys have been looking at my screen. Hopefully you've had a little bit of time to kind of think about this. So I'm just going to cold call on some folks, and I'm not going to take time to write the numbers down. We're just going to shout them out. So I'll start with Thomas. Thomas, what is the square root of 64? Cassett, are you with us? Guess not. All right, Aiden, how about you? Square root of 64.
8.
Good. And then when we negate that, we just get negative 8. All right, so Matt, square root of 225.
15.
All right, so when we multiply 15 times 15, we get 225. And again, it's positive just because there was no negative coefficient. Good. All right, Anthony, square root of 100.
10.
All right, very good. And then Campbell, square root of 121.
11.
11, excellent. Gannon, did you ever pick up with us? Are you on?
Yes, sir.
Awesome. Gannon, what's the cube root of 27? Speak up nice and loud, Gannon. 3, absolutely, very good. All right, and then 4th root, Stephen, 4th root of 256. Steve-O, you hear me?
Yes, sir. I'm just thinking.
Okay, good. No worries. And once these numbers start getting bigger, you guys, don't be afraid to think about smaller quantities, right? Like to break it down to where, not necessarily prime factorization, but hey, if I divide 256, if I cut that in half, right, what do I get? I get 128, which hopefully I recognize as a power of 2. Or maybe if I cut 128 down, I get 64. I really should recognize that as a power of 2, considering we did one earlier. So what you can do is you can use your past experience. Look, Stephen, if you will, at 64. And we talked earlier about how 64 was 4 times 4 times 4. And if I multiply 64 times 1 more 4, I get 256. So the 4th root of 256 winds up being 4 as well. And then what do you guys think the 5th root of 243 would be? That one's a little bit of a stretch. What do you all think?
7. No.
Well, 7 times 7 times 7 times 7 times 7 is going to be a ginormous number.
Yeah.
3. 3.
Winds up being 3. Okay? And I don't want you to have memorized the fact that, yes, 243 is 3 to the 7th power. But what you can do is you can recognize, you can say, oh, okay, you know what? If I divide that by 3, for example, that's 81. And hey, we talked about 81 a moment ago, and start using some experience, right? So let's start talking about estimation. you guys, you ever heard of the word or the phrase ballpark figure? If I said, hey, give me a ballpark figure, what does that mean?
Close to the number.
Yeah, just close to the number. Anybody have an idea of where that expression actually came from? It has to do with money, as do a lot of things, I suppose, in this world. The phrase ballpark figure is an old school phrase because what used to be the case was that an owner of a baseball team, he would be up in the press box, okay, and you know his income depended upon ticket sales, and so what he would do is he would stick his head out of the press box, and he would look around the ballpark, and he would see out across all the stands. And he would just kind of in his mind estimate or approximate, gee, I wonder how many people came to the ball game today, so that he could approximate or estimate how much money he was going to make, how much he was going to bring in revenue and ticket sales that day. That's called a ballpark figure. It's a rough approximation. He didn't get down and count every single ticket holder, but he would just kind of approximate it. So that's what we're going to do in this screen. That's what we're going to do in this example. So the square root of 105, Wilson, what's that really close to that I do know the square root of? Webster, what perfect square do I know that's really close to 105? All right, Perone, I'll kick it over to you since I didn't hear anything out of Wilson.
10.
Yeah. So you see, the square root of 100, I do know. The square root, the next one, by the way, would be the square root of 121. I do know that. And although I don't know what the square root of 105 is, since the square root of 100 is 10 and the square root of 121 is 11, Cullen, where would you say the square root of 105 probably falls?
In between them.
Yeah. And by the way, which one do you think, Robert, it might be a little bit closer to?
10.
Absolutely. It's probably going to be, a little bit closer to like 10.2. Maybe 10.1 and some change. I don't know. Because 105 is closer to 100 than it is to 121. You guys see that technique, how that works for approximating a square root? Give me some feedback, boys. I can't hardly hear anything out of y'all.
Yes.
Yeah.
Yes, sir.
Yes, sir.
All right. So how about cube root of 43? Well, let's think about the nearest perfect cube. I know that the cube root of 27 is 3. I know the cube root of 64 is 4. So the cube root of 43, although I don't know what it is precisely, I could ballpark it. It's probably in the neighborhood of maybe like what? What do you think? Maybe 3.4?
Yes, sir.
What is that? 16 away? There's a difference of 16 there, and a difference of 21 between these two guys. So it's likely going to be, like maybe 3.4-ish. How could I verify my answers? How could I check to see if these are good approximations?
Square.
Square 3.4.
Oh, okay, that's not a bad idea. So you could square 3.4 and see if it's close to 43. I was thinking a little bit more technologically savvy, maybe.
Use a calculator.
Yeah, whip out ye old calculator. Now, interestingly enough, how does the calculator know? Seriously.
Program.
Well, yeah, somebody wrote a program, though. How does that program work? I'll give you a hint. It works the same way this does, just a lot faster and a lot more efficiently. What they do is between 3 and 4, it works. And then they pare it down. So once they lock in the 10th place, then they say, okay, well, let's start hammering down on the 100th place and then the 1000th place. And obviously there's going to be a little bit more calculus involved. But for the broad strokes, that calculator is running a program that thinks in the same fashion that we thought here with this example. Okay? All right. For radical rule number 4. Ready or not, here it comes. Radical rule number 4. The square root of x squared. One of you brainiacs tell me, what does that equal?
X.
No!
X.
No!
X minus X.
Positive or negative?
X.
Did somebody just say that I had a square root equal to a negative something? No, no, no.
Is it
X.
X1 is no.
All right, I'll tell you what. We'll play ball with you guys that are saying X, because a lot of times I get argued with. Oh, Coach Morgan, you don't know what you're talking about. That obviously equals X. And I'll prove it to you. And so they say, I'll prove it to you by letting X be a particular number, okay? So won't you, I don't know, Jack, pick me a small positive number.
3.
All right, so they'll say, like, let X be 3, okay? And then they check to see that equality holds up. So we want to see, does the square root of 3 squared, does that equal 3? Okay, well, 3 squared is 9. And, of course, the square root of 3, or excuse me, square root of 9 is 3. So does 3 equal 3?
Yes.
Yes, and they say, Coach Morgan, you silly boob. Of course it does. You're wrong. And I say, well, wait a minute. 3 is not the only number out there. What about 0? And so they say, okay, let X be 0. And my supposition still holds, because 0 squared equals, I hope y'all are taking notes on this, by the way. 0 squared equals 0. The square root of which equals, and 0 on the left, 0 on the right. Ha ha, the day is mine. I'm right again, they say. And I say, oh, wait. 0 is not the only number. What other number might I need to consider? A negative number. So maybe we say, okay, like let X be negative 5. Okay. Square root of X squared. So we're going to say square root of negative 5 squared. And we want to know, does that equal negative 5? All right, negative 5 squared is 25. And then the square root of 25 is 5. 5 does not equal negative 5. And so their supposition breaks down with negative numbers. So here's the million-dollar question. I know you guys are smart. You can figure this out for me. What should I introduce in black on this supposition right here to make it true for all 3 scenarios?
Absolute
Who said absolute value?
Me, Campbell Gossett.
Campbell, you win $1 million. Congratulations. The check's in the mail. Because now, think about the right-hand side. It still holds up in the first 2 cases. But now, how about it on the right-hand side of that third case? What's the absolute value of negative 5? 5. So it holds up. Fellas, in black right there is radical rule number 4. The square root of X squared equals the absolute value of X. Okay? Matt, question.
I wasn't.
Oh, I apologize. Whoever it was, I misheard you.
So, with the power of the root rule, why wouldn't it just be X? Because 2 over 2 is 1.
Great question. And if you guys didn't hear what Jack was just asked about, he's tying in this last rule with his power over root, okay? So, for example, if I were going to take this right here and put it in exponential form, you would say x to the 2 divided by 2, which for us, we would think that equals 1.
1.
Right? So what we've now introduced is called a caveat. Y'all ever heard of the word caveat before? A little vocab word for you today. Somebody explain to me, what is a caveat?
An exception.
Yeah, that's a good way of summarizing it. Like, it's the power over root is a rule that works, but if it works in the following way, we have to add on a little bit extra. That extra little exception is that if I've got an even root, here's your caveat. Even root, okay, and even power, then I need to consider absolute value. Okay? Now, here's what I mean by that. And this is where we can kind of get lost in the weeds if you're not careful. Let me show you an example of what I mean by that. The whole purpose of absolute value right there is to ensure non-negativity. So if I gave you the example of the square root of x cubed, okay, the square root of x cubed, the way that that simplifies out is the square root of x squared times the square root of x, which we would say is the absolute value of x times square root of x. But then this absolute value becomes redundant. What is the purpose of absolute value? To ensure non-negativity. And yet, if I've still got x left in my radicand, what kind of radicands am I not allowed to have with a square root? Negative. So that's a non-starter. So what this means is that it is an implied domain restriction that x has to be greater than or equal to 0. And therefore, my absolute value signs are from the Department of Redundancy department. I don't need them. This would be my simplified result. Okay? Now, if I level, and by the way, power over root there works out the same way. If, as Jack suggested, we do 3 over 2, that's the same thing as 1.5. And then that splits up as x to the first times x to the 1/2, and that's x square root of x. So we get the same answer either way. But what if it's the square root of x to the 4th? Okay? What if it's the square root of x to the 4th? How would you split that up?
By 2. Wouldn't that just be x, 2x?
Not 2x, it'd be x squared. But the reason it's going to be x squared is because, again, you've got absolute value of x, absolute value of x, and so therefore that's absolute value of x squared. And again, we see this redundancy. Why do I square something? To make sure that it's not negative. Or rather, why do I take the absolute value of something? To make sure that it's non-negative, and yet squaring something does that for me. So this one would just wind up being x squared. Okay? So what we have to do is we have to be careful when we've got multiple powers in the radicand. We want to make sure that we simplify things out accordingly, and we're not putting something in that's not necessary. Okay?
So would it be incorrect?
To say what?
Like, let's say you put the absolute value signs there. Would it be incorrect, or would you accept it?
It would be bad form or unconventional. You might say it that way. You know how, like, if I said, hey, class, solve for me the equation 2x equals 6, right? And most everybody's going to tell me x equals 3. What if a kid said x equals 6 over 2? Is he technically incorrect? No, not at all. No more incorrect than somebody that says, oh, the answer is 3 over 1. But conventionally, how do we accept that answer? Just as 3. So conventionally, what we do is we try not to include absolute value bars if they are unnecessary. The only time we would consider leaving them in is when they become necessary. So like what I say, even root, even power, going back to our example here with part A, it is very much necessary when I've got the square root of x squared, or when I've got the 4th root of x to the 4th, because we want to ensure non-negativity. If I just said that and I know my time is up here, if I just said that the 4th root of p to the 4th was just p, then it would violate, like we said, it would violate that third stipulation. Well, what if p were a negative number? Then it wouldn't equal that. We would have to say, let me ensure non-negativity. All right? We're getting pretty deep into the woods, so I need to pause here, and let's regroup again tomorrow. Again, go through deltamath.com and do your couple of assignments practicing up. And then, of course, read in your textbook, fellas. They've got a lot of good explanations in 11.3 and 11.4 of your textbook, okay? All right. Well, hey, I very much appreciate y'all's attention today. I'll end it here. Live Jesus in our hearts. All right. Thank you, guys.
Thank you, Mr. Morgan. Thank you.
Second.
We have homework assignments.